So now that we know how to balance a chemical reaction, our next step is to look at our first reaction type, and that's going to be a precipitation reaction. Precipitation reactions are going to occur when we mix two solutions that have something dissolved in them and get a solid precipitate out of it. And we'll see what that means more as we go on. But first, we need to define what a solution is. A solution is going to be a liquid solvent, and in many cases we're just going to use water. So a solution is going to be any liquid solvent that has another substance dissolved in it. That's a pretty general idea, but we're going to make a key point here that being dissolved is going to be at the atomic level. So something is broken up into its individual molecules. So a common solvent that we're going to use is water. And when we talk about solutions of something, we're almost always going to be using water, okay? So you can basically consider, anytime I say solution, it's water. And something being dissolved in it, it doesn't really matter what the state of that thing is. We can have another liquid dissolved in water. We can have a solution of ammonia. Ammonia is also going to be a liquid. We could have salt dissolved in water. We could have sugar dissolved in water. We could have a gas, CO2 being dissolved in water. This is what carbonation is. It's carbon dioxide dissolved in water. And so let's differentiate between something being dissolved and something just being dispersed through water. Let's consider a little test tube that has some water in it. And let's say I put a bunch of sand in there and shake it up until the sand is really finely dispersed. Well, what would happen if I left that sitting for, let's say a full day? Well, after a full day, so the passage of time, so we're going to use an arrow to say the passage of time. After a full day, I'm going to have that water still sitting there. It's going to be mostly clear, and all of that sand will have fallen to the bottom. It'll separate out due to gravity. So that's not being dissolved. That would just be dispersed. If I had something like if I had salt instead, so let's erase this and let's make a salt solution. If I have a test tube, put some water in it, and I put salt in there instead, and salt is usually going to be white, so let's put it in white. I put a bunch of salt crystals and I shake it up until they're all dissolved. What's going to happen? Well, what's going to happen is that solution is going to clear up. Because once those salt molecules dissolve, they dissolve at the molecular level. And we can't see those molecules, so it becomes see-through. So we can see right through it. And if I leave this sit for a day, if I just let it sit for a whole day, or a week, or a month, or a year, well, it's going to stay just as clear. Those are going to stay dissolved because we have intermolecular forces at work. And we're going to learn more about those when we talk about states of matter. For now, we just want to understand what is happening when we dissolve something. So in this unit, the things we're going to be dissolving are going to be ionic salts. And so let's write out a chemical formula for an ionic salt dissolving. So I'm going to have NaCl, and I'm going to write its state here. I'm going to say S for solid. It is a solid, and I'm going to put it into water. I'm going to draw an arrow, and I'm going to write H2O above this to say that I put it into water. So that's the event that's happening to make this reaction go. And when that happens, that water is going to surround this sodium chloride crystal, and it's going to pull it apart into its individual ions, being Na+, all right, aqueous here. AQ stands for aqueous. So when we say aqueous, we mean water. So AQ stands for an aqueous solution, all right? And I'm going to have Cl-. So it's going to break it up into its two individual ions. So how does that happen? Well, let's use some colors here to help us. Let's put sodium in green. Let's put chlorine in purple. And let's draw out a sodium chloride crystal lattice. And then let's remember that when we're dealing with a water molecule, it has this polarity across it. So it's going to have these dipoles. And now remember, these ionic crystals stick together because the sodium has a positive charge, the chlorine has a negative charge. And Coulomb's law, remember Coulomb's law, says that there's going to be a force between these two opposite charges that's going to pull them together. There's going to be something pulling these together, like a rubber band wrapped around each of them. As they try to move apart, something pulls them back together. And so when the water surrounds this, when this goes into the water, well, this sodium is positive here, so naturally the negative dipole of the water molecule is going to want to face that. And so you're going to get a bunch of water molecules surrounding that sodium, all with that oxygen facing it. Likewise, these chlorines, well, the hydrogen part of the water molecule, that's going to face the chlorines. So you're going to get a bunch of these hydrogen molecules. It's a little crowded, but you get the idea. A bunch of these water molecules are going to surround those chlorines. And because this is a liquid, this stuff doesn't just sit there. These molecules are in constant motion. They're bumping around into each other. It's like a crowd at a rock show trying to go into the mosh pit. There's going to be people running into each other, bumping each other around all the time. And so these aren't still. So another water molecule bumps this guy, and he's going to move, but he's now stuck to that sodium. And so he's going to pull that off. That whole thing is going to come off together. I'm going to have the sodium pulled away, with a little positive charge, with the oxygens surrounding it. And it's going to be, if you can imagine, like the Beatles come to town and teenage girls just surrounding them. This is a dated reference, but if you've ever seen old videos of the Beatles coming to America, there's hordes of screaming teenage girls surrounding their car. As their car moves, the teenage girls move with it. And so that's going to be kind of what's happening in this solution. This sodium gets dissolved. This moves away, and now all of these water molecules surround this single sodium ion, and they all move together. And so this gets split up at the molecular level. And the same thing is going to happen with this chlorine. And so when something gets dissolved, it gets pulled apart at this molecular level. Because these atoms are too small for us to see, it just becomes see-through. But they're not always colorless, right? There's going to be some solutions that are going to absorb certain wavelengths of light. A great example of this is going to be copper sulfate. If I put solid copper sulfate crystals into water, stir it up so that it fully dissolves, and I'm going to break that up into copper 2 and arrow plus, and the sulfate anion, 2 minus. And so these are both going to be aqueous. Well, the copper naturally redirects certain wavelengths of light and allows blue light to scatter through it. And so the solution is going to look blue. If you ever see a copper sulfate solution, it's going to look very blue. It's like a really nice bright blue. It's a color I actually really like. But it's still going to be see-through. So I can still see through this. So my eyes here, I can still see through this solution. So it's got that blue color, but it is see-through. Okay? So then one last note. If I have something dissolving like let's say, let's use copper again. Let's say copper 2 chloride, CuCl2. And I put that as a solid crystal into some water and it starts to dissolve. Well, it's going to break up into that copper 2 plus, right? It's going to be aqueous. And the chlorine, Cl minus, the chloride anion, is also going to be aqueous. But remember our conservation of matter here. I have 2 chlorines in this copper 2 chloride. And so I need to have 2 chloride anions when this dissolves. And so when I model this out, if I model this in a little beaker here, then when I draw this, I'm going to draw copper 2 plus for every one Cu2 plus, I'm going to have 2 chloride anions. Okay? And then when I draw this out, I'm going to have the oxygen of the water molecule facing this. I'm going to have hydrogen of the water molecule facing the chloride. So with all of that said, there is one little caveat that we need to talk about here. And this is going to be the difference between a chemical change and a physical change. Now, we've talked about chemical changes versus physical changes. We've talked about a physical change being a change in some of the properties of a substance without changing its chemical structure. So it's like if I take H2O and I have it as a liquid and I put it into a freezer, well, it could freeze and become solid, but its chemical structure stays the same. Or a chemical reaction might be something like the combustion of methane, where I take methane and I mix it with oxygen, and when I change it, I fundamentally change those particles. Well, would we call a dissolution a chemical or a physical change? Well, it can really be argued both ways, and you're going to end up seeing this in different ways in different chemistry classes, and it's really kind of up to the instructor. And so we could say that since it's really Na plus Cl minus is a solid, since we could say that this is the argument for this being a physical change and not a chemical change. It's really just changing its state, right? And so there are instructors who say this would be a physical change then. And they further go on for a precipitation reaction, which is what we're going to study next, and they call that a physical change as well. But in this class, we are going to call that a bunch of malarkey, because we do have a fundamental change going on here. With this sodium chloride as the crystal, it's going to have specific properties, and as the sodium ions and the chloride ions, this is going to have different physical properties, and I can separate these structures at that molecular level. So I'm going to call this a chemical change. But this is something that you should keep in mind as you take other chemistry classes. You'll need to figure out what does that specific instructor decide on, because this is kind of a gray area. I will really accept both answers, but I call this a chemical change. By my definitions, this is a chemical